This training package explains how to model fracture mechanics problems in Abaqus, covering the theory and the modeling steps. The package includes 8 comprehensive workshops, ranging from modeling crack propagation in 2 and 3D specimens using the XFEM method to simulating fracture from low cycle fatigue. We have also developed a Python script that lets you extract crack length over time in Abaqus using the XFEM method. You will have access to the script explanation in PDF format. In this training package, we provide a lesson in PDF format to help you become fully familiar with the concepts of fracture mechanics. For example, the topics covered in this lesson include fundamental concepts of fracture mechanics, the difference between brittle and ductile fracture, the concept of the fracture process zone, FPZ, and other related subjects. We have also thoroughly explained topics such as linear elastic fracture mechanics, LEFM, along with its associated concepts, including energy equations, stress singularity at the crack tip, the stress intensity factor, SIF, and fracture toughness, detailing how they all relate to one another. Furthermore, key relationships are examined in detail, such as the connection between the J-integral and fracture toughness, and the interplay between fracture toughness, the strain energy release rate, G, and the stress intensity factor. This way, before you even begin tackling the modeling of fracture mechanics in Abaqus, you will be familiar with all the relevant concepts and equations. Additionally, we have also reviewed the methods for modeling fracture mechanics in Abaqus in the PDF file and have provided the necessary tips. This way, once you understand all the fundamentals, you will be prepared to go through the workshops and successfully model fracture mechanics in Abaqus. But you might be wondering what we do in the workshops. As we've said, we have 8 workshops. In video format, we've explained the modeling steps for each workshop in Abaqus step by step. In Workshop 1, we modeled crack growth in a 2D steel plate using XFEM. The crack growth pattern is shown in the figure. In Workshop 2, the simulation of a crack in a steel plate is examined using the classical method. This workshop also discusses the application of the contour integral criterion. In Workshop 3, we simulate crack growth in a 3D cylindrical steel model using XFEM. The maximum principal stress criterion is used to model the crack growth in this scenario. In the next workshop, we tackle a more complex problem, using XFEM in Abaqus to simulate crack growth in a 3D steel tube model. In Workshop 5, we use the XFEM model in Abaqus to examine crack growth in a bolt connection. This is considered a notable and relatively complex simulation problem. It should be noted that to simplify the model, the simulation is performed in 2 dimensions, 2D. In Workshop 6, we provide a step-by-step guide for simulating delamination propagation in low-cycle fatigue analyses using the VCCT method and Paris law. The example includes a rigid loading arm and 2 Lagrangian specimens, where the upper specimen is subjected to periodic tension. For clarity, all required details for implementing the low-cycle fatigue analysis are presented in the provided PDF. Moreover, the video tutorial shows in full detail how to model the components, edit keywords, submit the job, and extract the results. In Workshop 7, we simulate a tank with a crack, subjected to both internal and external pressure. This simulation uses the D-load subroutine to apply the load and the contour integral criterion to model the crack. The workshop concludes by showing how to extract the resulting J-integral value. In the final workshop, we revisit the problem from Workshop 1, but with a focus on post-processing the results. First, since it's not possible to directly extract crack length versus time in Abaqus, we developed a Python script that enables you to do so. Additionally, we show you how to extract other results, such as crack mouth opening displacement, CMOD, strain energy, and external work, and how to plot the corresponding curves for fracture mechanics problems. I hope that this information about the package has been useful for you. By using the theory and formulations presented in this package and its diverse workshops, you will master this subject. You'll be able to perform your own fracture mechanics simulations in Abaqus, whether you're tackling a standard static or fatigue problem, in either 2D or 3D. All the information you need is covered. For more details about the package, we suggest you click the product link in the description, and check for more information on our website.